Hi, welcome back to My Smart Learning with Mr. Meehan. It's a lesson for Year 9s with your physics topic on energy. It's useful for Year 10s and 11s because it's your GCSE science and physics. So last time we looked at energy transfer and we looked at something called specific heat capacity. Today we're looking at how we control the heat inside a building. So how do we heat our homes and how do we stop them from getting cold is the learning objective. So high five, remember your quick quiz, your recall quiz. So question 1, what are the 3 types of heat transfer? Question 2, which one happens in solids? Number 3, which one happens in fluids? Number 4, which can happen through a vacuum? And what do we call poor conductors? Now, they were the same ones I used last time when we did specific heat capacity, but these 5 questions are very, very important when we're looking at today's lesson, so that's why I've gone through them again. Right, so if you've had a go at that, if you pause the video and had a go at that, see if you got the answers right, if you haven't paused it. So number 1, 3 types of heat transfer. We've got conduction, convection, and radiation. Which one happens in solids? It's going to be your conduction. Conduction happens in solids. Fluids are gases and liquids, so that's going to be convection. And then which one can happen through a vacuum, which is empty space? That's going to be radiation, infrared radiation. And the last one, what do we call poor conductors? We call them insulators. Now this is very important when we're looking at heating our homes and preventing the heat loss from our homes. So how do we heat our homes? So obviously we're coming into summer, so the chances are you're not heating your home right now. You'd rather stay cool. It's not that hot though. In hotter countries, like let's say in Spain, it gets really, really hot. So you don't need to heat your homes in the winter. In the summer there. You actually try and keep your houses cool in the summer. Whereas in this country, we tend to have our heating on in the winter and we just tend to leave it switched off in the summer. So, but how do we heat our homes? Well, the easiest one is a log fire. Now most of us don't use log fires anymore because we don't tend to have like fireplaces that we use that are open like the old fashioned Victorian ways where you'd have a chimney and you have to get a chimney sweep because all that soot will build up and then have to climb up and clean all that soot to stop the or to allow the smoke to escape out the house, or else you'd be poisoning yourself. So log fire is an obvious one. Gas fire, so same thing in your fireplace, you'd have, instead of a log fire going on there, you'd probably have a gas fire in that place where there would have originally been a log fire in the chimney. Nowadays we don't really need chimneys because what's the point? Because most of our homes are heated by central heating where you've got a boiler. That boiler's got its own flue, or basically like a metal chimney in its own right. That flue takes any waste gases out of there, but it's the fire inside the central heating system that heats up the water and it pumps the hot water around your house. That goes to your radiators and your radiators radiate that heat out, warming up your home. And the other one, we've got electric heaters. So sometimes if you haven't got a gas fire or you don't have gas supplied to your home, you can just plug in your normal electric heater. And the other thing you can have is you can have a solar power to heat up your homes. So you can have either solar tanks, which are sort of solar panels that absorb the heat and then get the sun's energy warms up that water, and then you can use that hot water as a heating effect in your home or just as in hot water. But you've also got solar power cells, photovoltaic cells that you see on the people's roofs now, and that generates electricity. That electricity can be used to power electric heaters. Now, what do we mean by a temperature problem? Well, if you think about a piece of metal, it feels cold. You feel a piece of wood and it feels warmer, it doesn't feel so cold. Well, why is that? Well, they don't have the different temperatures. Well, what's happening is your warm hands is transferring the heat from a warm place to a cooler place. So there's going to be a greater transfer happening in the metal rod because the metal is drawing the heat away from your hands because it's going from a warm place to a cold place. This one doesn't have such a big gradient, so therefore it doesn't feel as cold. So metals feel cold whereas the wood feels warm. Metals are good conductors whereas the wood is a poor conductor, so we call it an insulator. Now, heat is the thing that always travels. I gave you that anecdote last time. So if you've got the door open and the heat is escaping out of your house, You don't say, Mum, or your mum doesn't shout at you, shut the door, you're letting the cold in. Because it's not the cold that's coming in, it's the heat that is escaping out of the house. Because it's the thermal energy transfers from a warm region to a colder region, i.e. from your house, it will escape out of the house, either through the windows or through the open door or so on. So by closing the doors, closing the windows, you're retaining the heat. But still, it's not 100% efficient. Heat will escape. So that's why we need thermal insulators. So what makes a good thermal insulator? Things like plastic, wood, ceramics, which is like pottery stuff, and air actually is a good insulator. So you want to keep warm when you're out snowboarding or skiing, so you wear warm clothes. You call it warm clothes, but what is it? It's basically good insulators. So the heat that your body generates stays closer to you and doesn't escape away from you, keeping you warm. Okay, so it reduces heat loss. Now, I need my assistant today. My assistant, I need you to do me a favor because I've forgotten to bring my little prop. So can you just run to the kitchen and get me the thermos flask in the bottom drawer? So, a thermos flask. What is a thermos flask? A thermos flask is a bottle that you can keep the drink either hot and it stays hot for ages, or you can have a cold drink in there with like ice in there and it'll stay cold for ages. So what's it doing? It's preventing heat loss. It's stopping heat from escaping or heat from going in, keeping that cold. Well, how does it do it? So we need to think about different things you can have on your thermos flask to, sometimes called a thermos vacuum flask. Thermos is the actual brand name, it's a company, I just call it Thermos. It's a bit like calling a vacuum cleaner a Hoover when there are other companies like Dyson now. Now we all call them Dysons obviously, but when I was a kid we used to always call vacuum cleaners the Hoover, but the Hoover is the brand name, they're actually called vacuum cleaners. So here is a vacuum flask, or thank you to my lovely assistant. So you can shut the door as well. Right, so we've got, this is my thermos flask. Okay, brand new awareness now, so hopefully Thermos will send me lots of free samples now. Thank you very much, Thermos. So Thermos is the brand name, but we call them vacuum flasks. How do they work? Well, if I open it up, I've got my cup and I've got this screw cap here. There's a screw cap, that's that bit that goes there. So this is made from plastic. Well, why is it made from plastic? Well, plastic is a good insulator, so the heat, it won't conduct very well, so the heat won't escape very much out of there. But I can have heat going out as radiation, because radiation can pass through that. Look, it's black, so it will absorb that infrared radiation and emit some of that radiation out of there. So I want to prevent that. So the thermos flask's weakest point is actually this, because every time I open my drink and pour it out, I'm allowing the heat to escape and some of the water to evaporate out from that, removing the heat energy, the thermal energy stored from here, and transferring it into the surroundings. So this is the weakest point. If I kept this closed all day and all night, I can pretty much keep this hot, this drink hot, my cup of tea or coffee, for pretty much 24 hours. Okay, so if you go on a picnic or go mountaineering, go for a long walk, this will stay hot for the entire day. Why? Why can't it just the heat energy inside the thermal energy, why can't it transfer out? Well, inside, if I take a cross section, if I cut through this, inside what I've got is a shiny lining on the outside of this glass bottle. And you can see it's kind of raised from the bottom, so it's not touching the side, so we don't get any conduction. Okay, and it might also be packed with some kind of soft material there to stop it from having any impact, but also that soft material, like some kind of polystyrene type material, will be a good insulator preventing conduction. Also the airspace there, this is a vacuum. So what's happened is it's a glass bottle inside, but when the glass was made, it's 2 layers of glass, and there'll be a point at which there's a seal where it's sucked all the air out between the gap, between the first layer and the inside layer of the glass, which means there's a complete vacuum. So if it's a complete vacuum, you can't get conduction, because conduction happens in solids, and you can't get convection, because convection happens in fluids, liquids and gases. So therefore I've cancelled out my solids, liquids and gases. So therefore no conduction, no convection goes out that way. But what can go out that way is infrared radiation. Now remember, infrared radiation in one of our lessons, it's just an electromagnetic wave. So it can just go through things, all right, the heat signature. But what you'd find is this glass bottle is actually covered in a foil, like a silver shiny surface. Now what you remember from your infrared lesson, silver reflects. So what happens is if any of the thermal energy, the heat, tries to get out by radiation, it reflects and bounces straight back into the bottle. So therefore retaining that heat energy, that thermal energy store. So it stays within inside the bottle. So that's how a thermos flask is designed. But like I said, there is a weak point, so it doesn't stay hot forever and ever and ever, because this bit here, what it's calling the cork, there will be some energy transfer. So I've got my lid there, so again it's got a silver surface there, so if any is trying to come out, it will reflect and go back in. So that's my thermos flask. But we need to think of these ideas about the thermos flask to think about your home. Your home is being heated from inside, but all of that heat energy can escape. Therefore your bills will be very, very expensive. So you want to make sure that your bills stay as low as possible. So how do we do that? Well, we're going to make sure that that heat doesn't escape. So you can see with this thermal imaging camera, you can see with the infrared camera where the heat is escaping. So where is most of that heat escaping? You can see the brighter sort of orange yellow bits are the bit and the red bits are showing you where the heat is escaping. Well, if you look, the brightest parts are in the roof, and most of our energy does try to escape out of the roof because hot air rises and the heating effect rises and it goes straight upstairs and then out the roof. And that's why sometimes bedrooms, if you got a one story or two story house, the bedrooms upstairs and the bedrooms above that get really, really hot because the warm air rises and goes through the house, warming up the rest of the rooms. So the upstairs tends to be hotter than the downstairs because hot air rises, remember convection? So you get heating effect goes straight out of the roof. Now you can tell a house that doesn't have loft insulation in the winter when it's snowing. If you walk down the street and you look at everybody's roofs, all the roofs that got snow on top of them are homes that have got loft insulation. And any roofs that are completely melted and you can see the bare roof, that tells you that the house hasn't been insulated. Well, why is that the case? Well, if you think about it, if it's insulated, the heat can't get up to the roof. So therefore that heat isn't melting the snow and the ice. Whereas a house that isn't insulated, the heat will rise straight into the roof and melt the snow, and the roof will have no snow on it. So you can see where most of the heat is escaping. Look, the windows, the door, the roof. Okay, so we need to make sure that your house is well insulated to reduce heat losses, and therefore we're not wasting energy, because then you'll have to, if you were wasting energy, your house will be getting cold too quickly, so you have to have your boiler on even for even longer. You'll be burning more fossil fuels, more gas, natural gas, therefore producing more carbon dioxide. Therefore you're going to be adding to the global warming climate change crisis. And at the same time, your bills will be astronomical. Your gas bills will be really expensive, which they already are anyway. So you want to make sure that your home is well insulated. So where does the heat go then? Most of it, 20%, okay, so through the roof. Another 36% through the walls, but it depends on your house. This house is a freestanding house, so this has got walls at the back, front, left side, right side. So this is a detached house. So if you've got a terraced house, for instance, you won't have a wall there and there because there'll be your neighbour's house on either side of you. So you won't be losing it because whatever they're producing will come into you and whatever you're producing will go into them. So it should even out. So it's only at the front and the back. So that'd be more efficient. So you'd be only losing half the amount if you were in a terraced house. So what, 18% if you're in a terraced house? If you're in a detached house, semi-detached house, only one of the walls will be losing it. So a quarter of that. So that will be what? So 18, 9. So you'd lose 9. You'd lose 9% from that. So you'd get what, 27% loss if it was a semi-detached house. Your floor, if you look, a quarter of it goes through your floor. That's why we put carpets down. And even 4% through your door. That's why you tend to put draught excluders down. And 12% through your windows. But it depends on the size of your window. Some houses have small windows. Some houses have huge windows. But then we need to think about what we're going to do. Now I've posted this PowerPoint and show my homework. So you can fill the tables in as you go along. And there'll be some questions that you can do and work on as you go through the slides. So our windows then. So our windows, if it's just a normal window, the energy will transfer straight through, mostly infrared, because it'll go straight through. So if you've only got one pane of glass though, some of it will go through conduction because the glass will absorb some of the heat energy and then it'll radiate it out. So, but most of us now will have double glazing windows as standard. So double glazing windows are two sheets of glass, and in that space between the glass can either be two things. It can be either very dead still air, or it could be a vacuum. So there's two types of double glazing, but the idea is you either got air trapped in there, which will reduce conduction, because remember conduction can't happen through gases, or it'll be a vacuum where you get no conduction, no convection. Obviously only radiation can go straight through. So double glazing windows are really good at reducing heat loss by conduction and convection. So they'll save us money on our energy bills. What about between the walls? Now the outside wall isn't usually just one layer of brick. It's usually got two layers of bricks, and you tend to have like breeze blocks, other type of bricks in between. But there's a gap. Now that gap in itself can act as an insulator, because air is a good insulator, so it prevents heat loss. But what would make it even better is if you pack that space with a foam, and we call that foam cavity wall insulation. So if you fill that space, if you basically drill a hole into the wall that side from outside, and you put a pipe in there, a bit like a hose pipe, and you squirt in lots of this foam, it packs it full of foam, and the foam becomes solid. It's not liquid foam. And then it just squidges and fits into that space between the walls. And that's known as cavity wall insulation. And that's really good at preventing heat loss as well, because you're preventing any conduction. You're also preventing any convection, because there's no movement of any air there. Whereas if you just got dead air space there, then you will get convection currents happening in there, so you will lose some of the heat energy. So that's a better way. What about if it goes through my roof? The obvious thing, the cheapest way to insulate your home, the most cost-effective way, is actually to have loft insulation. So you put some insulation in your loft. It's just a yellow foam, a yellow sort of fiberglass type thing. You roll it out, and it's like a blanket in your roof. So any heat that's trying to go out through the roof will be absorbed, any thermal energy will be absorbed by the foam, the loft insulation, and that's going to prevent your heat loss. What else have we got? So to prevent infrared then, we want to reduce infrared. Behind your radiators, if you put aluminium foil, literally behind the radiator on the wall, the heat should be coming out from the radiator into the room, warming up the room. However, if it bounces off the foil, it can reflect it back towards the room, because if there's a wall, obviously there's a wall behind the radiator, that wall will be absorbing some of that heat energy, and the bricks will be getting warm, and that heat can escape out to the outside. Okay, so using foil, and the same thing, you can use the same idea, having this aluminium type foil in the cavity wall insulation. So you packed it full of foam, but on the inner side, when you're building the house, if you line it with a foil, aluminium foil, then any infrared radiation trying to go through that wall will reflect and come back in. So, draught excluders. So the door, obviously you want to open and close it, so there has to be a tiny gap at the bottom and the top so the door can open and close. Well, that gap will allow, or cold air coming in, what will happen is the heat from the house will escape through that gap, okay? And the draft is caused because there's a hole somewhere else in the house, there's an opening, and the air will move in a direction like this. So the heat will be escaping out of your house. So what you can do is you can put this little bristles, screwed in at the bottom of the door, known as a draft excluder. So it's preventing that draft, so it's reducing the heat loss in the gaps in your house. So all these different ways. Really obvious basic ways. Obviously you close the curtains at night so nobody can look into your house, so they don't rob your house or whatever you, or obviously you want your privacy. But curtains prevent heat loss as well, because you've got radiation going straight out of those windows. You close your curtains, that heat energy inside the living room or whichever room will go into the curtains and warm the curtains up, and that heat will stay in the room because the heat from the curtains will dissipate back into the room, whereas you don't want it to go straight out those windows. So curtains are very, very important. Not just curtains though. Carpet with underlay is really, really important, because the heat can go straight through the bottom and into the ground, and then you're losing heat as well. So if we insulate our homes really, really, really well, and really think about when we design homes, how do we reduce energy losses, any heating losses, then you can reduce your gas and electric bills by a lot, and you can help the environment at the same time. So this then is a little animation that you guys can have a go at, because I'll post this and show my homework. It gives you an idea of how much it costs and how much money you would save. And this leads us on to, and there's a few little activities here that you can do with the true and false to see which one's which. Now, okay, let's have a quick go at this then. Double glazing keeps a house warmer because there is a layer of what between the panes of glass? What begins with A? It's a layer of air. Air is a poor what? Conductor. So it acts as an insulator. The trapped air reduces heat loss by conduction from the house. Okay, so you're going to reduce heat loss by conduction. Now there's another activity you can have a go at when I post this and show my homework. You drag and drop which one goes to where to reduce which type of heat loss. Now payback time then. So we'll finish off on this. Payback time. What's payback time? Is payback time when somebody's wronged you and you're going to get them back? No, I don't mean that by payback time. What I'm talking about is how long does it take you to get your money back if I spend some money on some type of insulation. Obviously it's going to cost me, we call it capital cost, it's going to cost me money to pay for it. But then eventually over every year I'm going to be saving some money on my bills, and then the number of years it takes for you to get that money back is called payback time. So payback time in years is the cost of your insulation divided by how much savings you make each year. So here's an example. My silver reflectors cost me £25 to put behind all my radiators around my house, but it saves me £50 a year. That's actually really good payback time, because that is only going to take me half a year. So within 6 months I've made my money back, or saved that money, because it's not going towards my bills. Okay, so £25 divided by £50 per year, I've got my payback time. What about these guys then? So your roof then, in my roof, if I put insulation in there, and it costs me £240, which is relatively cheap, but every year my gas bill has gone down by £80 a year, pretty much about six to £8 a month, then it'll take me how many years to make my money back from that loft insulation? Well, I do 240 divided by 80, it should take me 3 years. So 3 years it'll take me to get my money back, my £240, but then after that you're saving money, because that's not going towards your gas bill. What about windows though? Windows are only saving me £40 a year, but it's costing me £3,200 to put some double glazing in, which is, that's probably one of your most expensive costs. Double glazing, look nicer, they soundproof your house as well, so you don't hear all the traffic on the road and stuff, but they're expensive. And so therefore, 3,200 divided by £40, it'll take me 80 years to get my payback from that. So is it going to be cost effective? Is it worth me putting in that if I'm going to sell the house within a couple of years or so, I'm not going to get my money back on there, and if that price doesn't go into raising the price of the house, then what was the point? So that's something to think about. Draught excluders, it's cost me £50, but it's saved me £50. That's going to take me a year. So in 1 year, I've got my money back. So after that, I'm saving money. The walls then, if I put £500 worth of cavity wall insulation in, and it's saving me £100 a year, well, obviously, how many £100 will make £500 will take you 5 years. So 5 years to make my money back. So that's known as payback time. Cost effectiveness then is how much do you save each year depending on the cost of the insulation. So cost effectiveness then is 2, because it's the saving each year. I've saved £25 a year. It cost me, I've saved £50 a year. It cost me £25. So 50 divided by 25 gives me 2. The cost effectiveness of the draught excluder is 1. So the bigger the number, the more cost effective it is. So obviously you want the cheapest price with the highest amount of saving will give you the greatest cost effectiveness. So for instance, the double glazing is the least cost effective because it's so expensive. It's a bit like getting solar panels on your roof as well. How much money are you going to actually save, and how much electricity are you going to generate, but how much did the solar panels cost you in the first place? So are they that cost effective? And what about if you move home as well? So here's another activity for you. If you can organize these in the right order, okay, I'll send this on Show My Homework for you guys to have a go at. And there's a quick quiz, 1 to 10, with questions that you can have a go at. You've also got exam style questions, and you've got the key points to make a note of. Okay, so year 9s, you've had your first half of the lesson was to watch this video. The second half of the lesson is for you to make your notes from your caboodle textbook, or use the Key Stage 3 BBC Bite Size that I'll put the link on to show my homework as well. Use that to make notes. There's questions on there that you can have a go at too. So either use the bite size or use the questions on the PowerPoint there, but they're also on the caboodle textbook, and the notes are on the caboodle textbook. Make sure you got your notes, you got your exam style questions and key points done, and then hopefully you've learned something today at My Smart Learning. Hope you guys are keeping safe and keeping well. And I forgot to give you your virtual high five, which you cannot buy in the shops, although the shops might be opening back soon, but then you still won't be able to buy them in the shops. So thanks for watching till the end. Take care for now, and I'll see you very soon. Virtual high five.